Okay, so let us begin today's tutorial. Now, this is week 9, tutorial week 9. So, again, similarly, like last week, we'll be first solving some practice problems of earlier sets, and after solving those 10 problems, I'll come to the current week's assignment problems as well. And most of the problems we'll see that they are common in both of the sets. So some of the problems will already be solving when we are doing this practice assignment, and then the remaining set of problems which are extra in the current or present week's assignment, that we'll also discuss towards the end of this tutorial session. Okay, so let us begin. So the first question is, two globes contain 2 moles of oxygen and 3 moles of hydrogen at same temperature. A valve connecting the two globes is opened and the gases are allowed to mix without any reaction. Then calculate the change in entropy when given the R value is in joule per mole Kelvin. First of all, let me just write down here that this is that assignment that we are discussing now is what do I say, earlier, not earlier, practice set of problem. This is not the current one, but some of the problems are exactly similar to the current assignment. So let us first try and understand this first question. So as we can see from the question number 1, that this is basically based on two ideal gas, which is in this case oxygen and hydrogen. So they are initially they are contained in two different containers and they have the same temperature but different mole numbers and different gases. Now when the valve that is actually joining these two containers and separating them, when that is opened, so then the gases are allowed to mix without any reaction. So then oxygen and hydrogen, they mixes together. So as a result there will be a change in entropy, right? So that change in entropy you need to calculate. So let us now start calculating this and see where do the answer end up at. So problem number 1 is, this is the practice set of assignment I am solving now for week 9. Okay, so question number 1 is basically the heading should be entropy change for mixing of two different ideal gases. Now this word two different gases is important because later on, just in the next question, you will see that why these two ideal gases need to be different and not the same. Because in that case you will see that there will be no entropy change if we are mixing the same kind of gas from two different containers. So this calculation is only valid for two different ideal gases mixing, right? So without we'll elaborate this different or same part later on, but for now just start solving this, taking two different gases and they are both ideal gases and they are mixed together. So what happens and what is the change in entropy in the mixing process? So let me just, for a reference picture, draw a simple diagram of how this thing, the problem looks like. That this is your container 1 which has gas 1 and this is your container 2 which has gas number 2, which is in our case is oxygen and hydrogen, right? So now it is mentioned in the question that both of the gases are at the same temperature, and because there is nothing specifically mentioned, so you also assume that both of the gases are in the same pressure. So pressure and temperature is same in both of the containers. Okay, now what are the other informations needed here? First of all, volume. So volume of the two containers we here take to be different, right? So this container has a volume of V1 and this container has a volume of V2. Similarly, the number of moles of gas in container number 1 is, let's say, N1, and the number of moles in container number 2 is N2. So in our question it is mentioned that oxygen is of, I think, Oxygen was given 2 moles and hydrogen was 3 moles. So for oxygen, the number of moles N1 equal to 2, and for hydrogen, which is gas number 2, the number of moles is equal to 3. So these are given in the question, and also mentioned in the question is that they have the same temperature, but we also assume that they are in the same pressure because there is nothing specifically mentioned, and we can assume that. And after, so this is before mixing. So this is before mixing of the two gases. Now when the valve, that is, let's say there is a valve that is actually connecting these two chambers, which is closed in this case, okay, so they are separated from each other. Now if the valve is opened, so what happens is that there is no division as such between the two containers, so this becomes a one single container, and the gas from two sides mix together in a single compartment. So this is the after mixing state, and because there is no chemical reaction, nothing, so we again say that the pressure and temperature remains just the same as it was before mixing of the two gases. So pressure and temperature of this chamber is, of this compartment is again P and T, but what changes is that now the total mole number becomes N1 plus N2 because two gases moles, they add up with each other. This is the extensive quantity. Same happens with volume. Volume is also extensive, so the two volumes, they merge together, so the total volume becomes now V1 plus V2. Okay, so this is before mixing and this is our after mixing. Okay, so we also, for our reference, we say that before mixing, the first gas has an entropy of S1 and the second gas, which is hydrogen, has an entropy of S2, and we assume that after mixing, the total mixture of gas in this container has a entropy net value of S, right? So now what do we have to calculate is that we have to calculate the change in entropy because of the mixing of two gases. Now if you see that change in entropy by mixing has two parts. One is gas number 1 goes from this initial entropy was S1 to the final mixture entropy is S, right? So this is S. And second happens for gas 2, that gas 2 entropy goes from the initial before mixing value was S2 to final value of the mixture is S. So two change happens. So for first gas, the change in entropy you can tell as delta, you can mark as delta S1, which is nothing but your final entropy minus initial entropy. And for second gas, the change in entropy is delta S2, which is again the final entropy minus the initial entropy S2. So you have the entropy change for gas 1 is delta S1 and the entropy change for gas 2 is delta S2. So your final total entropy change, so total change in entropy of the mixture equal to delta S suffix or subscript mix, means the change in entropy of the whole mixture. Delta is equal to the addition of these two contributions, delta S1 and delta S2, because entropy is an additive, is an extensive quantity, so it will be additive. So you have to add the entropy change for gas 1 and the entropy change for gas 2 before and after the mixing, and the total contribution gives you your net entropy change for the mixture, which is delta S mix. So this now becomes makes our problem simpler, that we have to just separately calculate what is delta S1 and what is delta S2, and then by adding that we can get the net change, right? Now then generally speaking, how do you define your entropy change generally? So just one moment. Yeah, so let us go back to what we are solving. So right now how do you define your change in entropy? So general sense, if you write ds equal to, you know, dq by t, right? So entropy change, infinitesimal change, d is equal to small amount of heat absorbed dq divided by the absolute temperature T. So your delta S is basically integration of ds, the total contribution of change in entropy if you have to take, then this is just dq by T, right? Now you know that dq from the first law of thermodynamics, it is du plus dw. So this is the first law of thermodynamics. Now you know that U, the internal energy, is a function of temperature. Okay, and it is a state function. So if dt equal to 0 or the temperature is constant in the process, which is in this case, we saw from the question, it is mentioned that before and after mixing, the temperature of the gases individually or even the temperature of the whole mixture does not change at all. So the temperature is constant in this process. So dt equal to change in temperature equal to 0. And because u is a state function and it is a function directly of temperature, so if temperature is not changing of that state, then u will not also change. So u is equal to also constant and du equal to 0. This is the condition that you get if it is mentioned in the question that there is no change in temperature, then du should be 0. So simply you will get du equal to 0 plus simply your pdv. Pdv is equal to your work done, which is non-zero in this case. Now if you have to further, so you can replace this dq by simply pdv by T now, right? Now as per the question, it is mentioned that the pressure and temperature both remains unchanged in the mixing process. So how do you then do this integral? So what you do in this case is basically you use your ideal gas equation, because in the question the gases are all ideal gases. So you know that is PV equal to nRT. So P by T becomes nR by V. So sorry, there is a misunderstanding. Maybe we should not have to consider that P is constant as well. Just as per the question, take T to be constant. So P can be varying because you can see from this relation that P has a direct dependence on 1 by V. So because volume is changing, so pressure has to change because temperature is otherwise fixed. So in our case, we only consider that we do not mention anything about the pressure. Right, there is no explicit mention about the pressure in the question, so we also do not do that. We just talk about temperature because temperature is certainly said to be constant individually before mixing and also after mixing of the total mixture. So this is P by T is equal to nR by V as per the ideal gas equation. Now you just replace that here, that P by T is nR by V dV, and your initial volume, if it is Vi to final volume is Vf, then the integral limits are that. So nR is constant, so it is outside integral. N is the number of moles, by the way. So this is nR ln V from Vf to Vi. So this delta S now in a generalized formula where the temperature of this process is constant. So your delta S becomes in the change in entropy contribution only comes from the change in volume, which is like nR ln Vf by Vi, where the volume changes from initial Vi to final Vf. So this is your change in entropy formula in a general sense for ideal gas when the temperature in the process is not changing. So that we can apply individually for each of the gases, gas 1 and gas 2. So if you have to calculate delta S1 similarly, so you can just write it is N1 because the number of moles for gas 1 is N1. So N1 universal gas constant R, then ln of the final volume becomes the total volume of the mixture, which is V1 plus V2 divided by its initial volume was V1, right? So this is for gas 1's entropy change, which has changed from volume changed from V1 to V1 plus V2, and the mole number changes from N1 to N1 plus N2. Similarly, for gas 2, we can also, because that is also an ideal gas, hydrogen. So this is the number of moles is different. N2 are, then the initial volume and final volume are. Final volume is again same V1 plus V2, but the initial volume is now V2. Okay, so this is for gas number 2, where the volume V2 changes from V2 to V1 plus V2, and the mole number changes from N2 to N1 plus N2. So these are the two contributions. Now the entropy change of the whole mixture is just, as I said, delta S1 plus delta S2. So now we elaborate that further. So N1 R ln of V1 plus V2 by V1 plus N2 R ln of V1 plus V2 by V2, right? Now here's the twist, that in the question, if you observe carefully, that they have mentioned the mole number, that is N1 and N2 of the gases, but there is no mention about the volumes explicitly. So we don't have the information about this V1 and V2 everything, but we do have the information of N1 and N2. So the trick we need to use here is that we have to convert these unknown terms into known terms, so that we can finally calculate our delta S mix. So that is again easy, because by ideal gas, even individually oxygen and hydrogen is ideal gas, and their mixture will also be an ideal gas in itself, because that is a mixture of two ideal gases. So by using the ideal gas relation, and what you get is that this is your, for oxygen gas, your P1 V1 equal to N1 RT, and for hydrogen gas, this is your P2 V2 is equal to N2 RT, and a mixture of oxygen and hydrogen, which is again an ideal gas, that is P V1 plus V2 equal to N1 plus N2 RT. Okay, so now here comes the question, that here it will be useful that your P1 equal to P2 has to be P, because the pressure is not changing in the question. Okay, maybe the pressure and temperature not changing, and only the volume and the mole number is changing. So from there we can extract this thing, that your V1 plus V2 is equal to N1 plus N2 RT by P, and similarly from here V1 equal to N1 RT by P, and V2 is equal to N2 RT by P. So you get N1 R ln V1 plus V2 is basically N1 plus N2 RT by P, into V1 is P by N1 RT, plus the second term is N2 R ln of N1 plus N2 RT by P, into V2 is P by into RT. So this and this cancelling out. Okay, so this is delta S mix equal to, now it has all in terms of, it is all in the known terms, which is N1 R ln of N1 plus N2 by N1 plus N2 R ln of N1 plus N2 by N2. So this is your entire delta S mix, right? Now once you have obtained the main formula, we can just replace the values that you know, like N1 is 2, so this is 2 times R ln of N2 is 3, 2 plus 3 by 2, plus N2 is 3 R ln of 2 plus 3 by 3. So you get 2 into R value is 8.31 joule per mole Kelvin to ln of 5 by 2 plus 3 into R is 8.31 into ln of 5 by 3. So what you get is basically if you take your calculator and calculate the ln values for these different parts, you will see that this is 2 into 8.31 into 0.92 plus 3 into 8.31 into 0.51, which is basically giving you 27.8 joule per Kelvin. No mole, because mole number you have already multiplied. So this is just joule per Kelvin. So getting a result of 27.8 joule per Kelvin. Now this is a correct answer, but this answer does not match with the options that is given in the question, but I think that can be a mistake in the options. Otherwise, because they are mentioning the answer to be 19.35, but the calculation is right. I think you can check for yourself, and the formula you are using also right. So you can check for yourself whether we are getting the same answer and it is matching or not. But the idea of the entropy change for the ideal gas mixture is the one that I had just discussed below. Okay, so this is done. Now question number 2 is about two globes contain oxygen gas of 3 moles and 5 moles at same temperature. Then a valve connecting the two globes is opened and the gases are allowed to mix. Then calculate the change in entropy given the R value is 8.31 something. Now this is a trick question, because after the last question you will be tempted to just calculate the thing using the same formula that we had just done for question number 1. But there's the trick that for two gases, that was what I was discussing earlier, that if you have the mixture of two ideal gases which are identical to each other or basically the same gas, then the entropy change will not be following the calculation we have done previously. That is only valid considering the fact that both the gases you are mixing are different gases. But for identical gas mixing, always the entropy change will be 0. So first of all, let us mark our answer that this will be 0. So in this case, for ideal gas mixing, delta S mixture is equal to 0 because both are oxygen gases, they are identical gases you are mixing together. So this thing is called Gibbs paradox. This is a very famous statistical mechanics problem, which is a paradox because we have just seen that using the formula for two different ideal gas mixing, there is a entropy change, right? But then why when like combining or mixing two identical gases, why the entropy change is has to be 0? How does these two align together, or how can we resolve this paradox? So that is the idea. So I will not go into much detail about what the paradox is or anything, because that is a lecture content that will be discussed, or that is already discussed in the lecture material. But I will just, for the sake of this question, I will give a brief explanation that why we are calling or we are saying that your delta S mixture is equal to will be 0 if we are mixing two identical gases. So this is called Gibbs paradox. This is called Gibbs paradox, which is basically is that this is a problem of statistical mechanics, that it says that mixing two ideal gases which are identical to each other, the change in entropy delta S mix equal to 0. But then why we are calling it a paradox? Because why paradox? Since earlier, as per earlier known calculation of delta S mix, people used a semi-classical approach or semi-classical derivation, which actually considered the calculation by default taking the particles to be distinguishable. So as per the earlier calculation of delta X mix, using a semi-classical approach, the particles were by default taken to be distinguishable like classical particles. Okay, and because of this consideration, I'm not going to show you the derivation of how this entropy expression is coming, because that you can find from the lecture materials or any other book or anything. But the resource, as per the following the resource, you can find out that considering when the particles are already taken in the calculation to be distinguishable, the calculation result will give you an entropy expression for ideal gases as S equal to nk, where n is the number of moles, k is the Boltzmann constant, to ln of volume times 2 pi mkt by h squared to the power 3 by 2. This whole thing is in the argument of ln, plus 3 by 2 third bracket close. Okay, so this is the entropy expression for ideal gas when the particles are taken to be distinguishable in nature. Okay, so then as per this formulation, if you go by, so then initial total entropy S initial is equal to the summation of the individual gases entropy, and for our ease we consider that both the, because now try to calculate that for mixing two same ideal gases by this formulation of distinguishable particles. If you go by, then we, for our ease, we can consider that both the gases are same already, but they both also have the same volume and same mole number, so that otherwise we could also take different mole numbers n1 and n2 and v1 and v2, but that just makes the calculation a bit more longer. So we would not want that, because we just want to have an idea that why this paradox is coming. So we just for simplicity consider that both of the gas compartments of the two same gases, okay, so same gases on both sides, and also we for simplicity can consider that both of them has the same number of moles and the volume. So n and v is the same, and pressure and temperature is already the same, right? So in this case, the initial before mixing case, the total entropy for 1 and 2 is in S1 plus S2, which is in this case S1 will be equal to S2, because if your n is similar, v is similar, and all other quantities are by default common, so obviously that there is no difference in the entropy value from 1 to 2. So this is S1 is equal to S2, so this is basically your 2S1, right, which is 2 nk ln of volume times 2 pi mkt by h squared to the power 3 by 2 plus 3 by 2. Now final, when they are mixed together, final entropy for mixture, let's call it SF, that is equal to, now the number of moles has changed from n to 2n, and the volume has changed from v to 2v, because they have merged together, right? So by using this same formula, now replace this 2n by 2nk ln of, now replace this v by 2v, to other things remain same, 2 pi mkt divided by h square to the power of 3 by 2 plus 3 by 2. So because there is a ln term, so we can always take, because you know that ln x into y is nothing but ln x plus ln y. So you can separate or disintegrate like that. So here we'd like to do the same to this case. We'd disintegrate out this 2 part from the rest of the parts. Okay, so basically that will give us 2nk ln 2 plus ln of v into 2 pi m kt by h square to the power 3 by 2 plus 3 by 2. So if you look carefully, that this term multiplied with the rest of the terms is giving you nothing but your SI, because that is the same expression of SI, right? So this term multiplied here coming here is your SI. But you have an extra term that is remaining here, which is extra from the SI contribution, and that we can write as 2nk ln 2 plus the whole other term is SI. So SF is this thing plus SI. Now this additional term is basically your SF minus SI, which is your change in entropy because of mixing two same gases, is equal to 2nk ln 2. Now because n is a mole number which is positive, k is also positive, and ln 2 is also a positive value, so this is greater than 0. That means your final entropy is greater than your initial entropy. So as if it is, this calculation is showing us as if that by mixing two ideal gases, you are basically after mixing you are increasing the entropy in this process, but which is actually not true or paradoxical, because you are mixing the same nature of gases from both sides. So there should be essentially no entropy change, right? So then why we are getting a finite non-zero entropy change? So this is the idea of this paradox. Why gives I think around the year of 1875 he first identified this paradox, that mixing identical gases our entropy change should be 0, but by following this formula or this calculation we are still getting a non-zero entropy change. So where is this additional non-zero entropy change term coming from, and how to resolve this paradox? So this was when the idea was modified, that formulation was modified, that the calculation approach we are starting about was entirely wrong from the starting, because we were taking distinguishable particles, right? Like we are taking the particles to be distinguishable. That is a wrong idea, because in quantum world, especially when you are talking about two identical gases, so their particles are actually not distinguishable, they are indistinguishable, or they are all identical to each other. So in that case, the calculation will be slightly different for the entropy, because otherwise if you do not take into account the similarity or identical nature of the gas particles, you will be overcounting the n molecules separately, because n molecules right now for the gases are all n molecules from left side are same as the n molecules from the right side, so they are not different from each other. So basically in the calculation you need to take care of the fact that you do not overcount the molecule number n from gas 1 and gas 2. So by considering that idea, that we have to consider for ideal gas identical gas mixing, that the particle should be indistinguishable. So now by this modification, that indistinguishable gas particles from 1 and 2, we can modify the formula of entropy that we are getting. So this modified entropy is basically given, again I am not deriving how this is coming, you can find it from any resource material, but the expression is nk ln of, now instead of v we have v by n inside, because you have to ensure that you do not overcount or repetitively count the similar gas particles from both sides. So that is why you have a n factor coming down here. Now this is again the same 2 pi mkt divided by h square to the power of 3 by 2 plus your 5 by 2. Okay, now following this, let us check whether the paradox is resolved or not. So here what I said is that but delta S mix for identical gas should be 0 for identical gas mix, this should be 0, but this is coming as non-zero. So this is the idea of the paradox. And how to resolve this? To resolve the paradox, we have to take into account that the particles from the two compartments of gases are indistinguishable particles because they belong to the same gas. Now the modified entropy looks like this. So now again we calculate similarly what is your initial entropy and what is your final entropy. So initial entropy is again S1 plus S2 equal to 2S1, which is 2 nk ln of V by N 2 pi mkt by h square to the power 3 by 2 plus 5 by 2. But the final entropy SF equal to, now your n should be changed into 2n, so this is 2nk ln of V should be changed to 2V and again n to 2n, so 2n to cancelling out into 2 pi mkt divided by h square to the power of 3 by 2 plus 5 by 2. So by comparing, you can see this value and this value is exactly same. So your SI equal to now SF. So your delta S mix equal to 0. So now the paradox is resolved, that you are getting that the mixture change in entropy for the mixture of two same gases is coming as 0. Only the problem was that earlier the calculation did not involve the consideration into account that the gas molecules from both the compartments are identical or indistinguishable because they belong to the same gas. Now this was the idea that why the question answer here delta S mix should be 0. Unlike the problem that we had discussed before this, that had two different gases, oxygen and hydrogen, because of which you got a non-zero entropy change, but in this case your entropy change should be 0. So your delta S mix becomes 0 now. So you are done with question number 2 again. Let us mark this and go to question number 3. So question number 3 is that two bodies of equal mass and thermal capacity of 0.8 joule per Kelvin, so this is your heat capacity C, and their masses are identical, so M1 equal to M2 equal to M, let's say, are at two different temperatures. T1 is 100 Kelvin and T2 is 200 Kelvin. They attain the same temperature on being placed in direct thermal contact. They are attaining the same temperature, let's say after they are in thermal contact, their final temperature both of the bodies is T, because now their temperature has been equilibrated. So that we already know that if you put a hot body in contact with a cold body, they will exchange heat and eventually they will reach a thermal equilibrium where both of the bodies will be at the same temperature, which is T in this case. Now calculate the change in entropy by that. So this is a simple problem of calculating change in entropy, right? Only you have to consider the change in entropy for temperature change for both of these two bodies. Individually you have to consider their entropy change, and then the net entropy change will be a summation of entropy change for body 1 and the entropy change for body 2. So let us go and solve this. So this is question number 3, which is saying that both the bodies have the same mass, M1 equal to M2 equal to M, and they have the same heat capacity, C1 equal to C2 equal to C, which is 0.8 joule per Kelvin, right? And temperatures are different, T1 equal to 100 Kelvin and T2 equal to 200 Kelvin. So this is the hot body and this is the cold body, T2 is greater than T1. Now when they are in direct thermal contact, so there will be a thermal equilibrium reached after some point. So in direct thermal contact, they will reach thermal equilibrium they will reach thermal equilibrium. So basically here, let's say after they have reached thermal equilibrium, both have the same temperature T. So the condition for thermal equilibrium is that condition for thermal equilibrium is that heat released by hot body will be equal to heat absorbed by the cold body. That is natural because the hot body will release heat and its temperature will be lower in the final equilibrium state, and the cold body will absorb that amount of heat that is released by the hot body, and eventually its temperature will rise, and eventually they will reach a temperature which is same for both, and that is intermediate in the sense that the hotter body will have a decrease in temperature and the cooler body will have an increase in temperature. So they will reach a equilibrium temperature which is same for the both bodies eventually when they reach the equilibrium. So by this case, you know, the formula of heat is basically mass times heat capacity into the change in temperature, right? But in our case, the heat capacity, so basically the heat capacity is generally given in joule per some mole Kelvin or joule per, let's say, kg Kelvin, like in terms of normalized by mass. But in this case, it is just joule per Kelvin. So we can, for simplicity, consider that the mass is unity for both the cases. Also because in the question it is mentioned that both the bodies has the same mass. So because our C is just 0.8 joule per Kelvin for both, so we can consider that our mass is unity, right? So assume that the mass is unity and m1 equal to m2 is both similar, so both are unity. So mc dt, in this first of all let us write mc1 m1 c1 because we consider the one body has a mass m1 and it has a heat capacity of c1. So in this case the change in temperature, let's say, is dt1, and the second case for cold body it is m2 c2 and dt2. Now what is dt1? It is the temperature change in this equilibrium process by the hot body. So the hot body is going from temperature initial T1 to the final temperature of T, obviously because it will release heat, so this final temperature T will be smaller than T1. So you will get the temperature change is T minus T1, right? And the other case is M2 C2, and in this case the cold body will be going from temperature of T2 to a final temperature of T, where the final temperature will obviously be greater than the initial temperature because it absorbs the heat. So then it becomes T minus T2. But because you have to take care of the sign and T minus T1 makes it negative, so to take care of that we just take a positive change in temperature, so that is just T1 minus T, because this is a change in temperature value, we do not want it to be negative, and because of this we take this is T1 minus T, because your dt has to be positive in both the cases, otherwise this will not be identical. Now in the problem it is mentioned that both the m1 and m2 are same, so this will be cancelling out, and also the heat capacities are same, so c1 c2 is also cancelling out. So from both sides you can gather that this is T1 plus T2 equal to, this goes to the other side, so this is 2T. So your final equilibrium temperature is T equal to T1 plus T2 by 2. So this is your final temperature of the at equilibrium, and each of the bodies will have the same temperature T. So once you obtain that, now you know that your change in entropy delta S, I have already I think shown this formula earlier in the past week's assignment, but I'll again show that this is ds is basically dq by t, and in this case it is solely change, there is no work done that is involved because no volume change, nothing is mentioned, only a temperature change is happening. So only du plus p dv is dq as per the first law of thermodynamics. So then dv is equal to 0, so there is no work done because no volume change, nothing is done in this case, only temperature is changing. So if temperature is changing or dt non-zero, so du the change in internal energy will also be non-zero, so that is equal to du by t, and you know that du has a formula of cv dt or mcv dt if it is normalized by mass. So your m and cv, if they are constant, so you are basically getting from changing from temperature Ti to Tf, you are getting mcv ln of Tf by Ti. So this is your change in entropy by a change in temperature from Ti to Tf for a body of mass m and a specific heat capacity of Cv, right? So this is your constant volume specific heat per mass. So by following that, your total change in entropy in the problem delta S will be delta S1 plus delta S2. So change in entropy for body 1 and the change in entropy of body 2. So because m1 equal to m2 equal to m, so this is just m times Cv. C is also common for both of them, so Cv is common. Then ln, for the first body, the final temperature of the equilibrium temperature is T and the initial temperature is T1. Now for the second body, mass and heat capacity are identical for both, so mCv. The final temperature is also identical T, but the initial temperature is different, which is T2. So if you further simplify and take common mCv, then this is ln of T by T1 plus ln of T by T2. So this is mCv. Ln of A plus ln of B is basically ln of A times B. So that is what you will get, that this is T squared by T1 T2. This is mCv. And because ln of some x squared is equal to nothing but 2 ln x, because this power will come to the front. So this is 2 mCv ln of T by root over T1 T2. So this is your final delta S. Now you put the values to calculate, and as there is no mention about the mass in the question, we take the mass to be unity. So m2 into 1 into the heat capacity is given in joule per Kelvin unit into ln of the final temperature. We have to calculate that by this thing that we got earlier, that the final temperature of the equilibrium T is T1 plus T2 by 2. Now you got in the question that T1 is 100 and T2 is 200. So this is 300 by 2, that is 150 degrees centigrade is the final temperature. So now here you have to use the absolute value. So final temperature 150 means 150 plus 273 divided by root over of, again 100, T1 is 100, so 100 plus 273 is 373 into T2 is 200 degrees centigrade, which is 200 plus 273 is 473 Kelvin. So this is 473, and the whole thing, if you take your calculator and calculate this, so you'll get a value of 0.094 joule per Kelvin. This is your change in entropy in the question. So we match our answer. .09 is the answer number, option number B. So option number B is the correct answer, right? Okay, so question number 3 is done. Then question number 4 is that the internal energy of a system is given by U equal to A P squared V, where A is a positive constant. Then find the equation for adiabats in PV plane. So you have been given the internal energy expression, which is a function of P and V, and A is a positive constant in this case. And you have to find out what is the equation for the adiabatic formula, that is, and you have to express that in PV plane. That means the whole equation will involve only P and V, right? Now how to do this is very simple, because they have mentioned equation of adiabats means you have to enter the condition of a system or a process to be adiabatic. So let us do that. Question number 4 is U equal to A P squared B, and A is a constant which is greater than 0. Now for adiabatic process, as they are mentioning in the question that they want the equation for adiabat. So for adiabatic process, your heat exchange is equal to 0, and dq equal to nothing but du plus pdv, right? That is 0, because that is the first law of thermodynamics, dq equal to du plus pdv. Now in the question, u is given. So du you can get d of a p squared v plus p dv equal to 0. Now this is because a is a constant. So first derivative you can take on p and keep the v constant. So this is a partial derivative thing, you know, already know. So this is giving you a times 2p dp into v plus, now keep a and p squared. A is already constant. Now take p squared to be constant and only derivative on v is dv. So this is plus p dv equal to 0. Now you are getting, so this dv and dv here taken together and dp is separate. So this is 2a pv dp plus a p plus 1 into p, because this is a p square and this is p, into dv equal to 0. So we take to both the sides separately, a pv dp equal to minus ap plus 1 to p dv. Now this p and this p is cancelling out. So taking similar terms to one side, like dp by ap plus 1 equal to minus dv by 2av. Now because this is ap plus 1, so we can consider ap plus 1 equal to y or a dp equal to dy. So you can take this a to this side, so this becomes a dp. Now you write this as dy by y equal to minus dv by 2v. Now if you take the integral on both sides, you get ln of y equal to minus half ln of v plus a constant, which is an integration constant. Now because both the sides are ln, so we take this constant to be ln of capital V, let's say, where b is another constant. This is just to simplify the whole expression, because so that all the ln terms can be combined together like that. And this is basically ln y is, now y is ap plus 1, so this is ln of ap plus 1 equal to minus ln v plus this 2 times constant. So we first of all we absorb everything as a constant. So 2 times a constant is also a constant term, divided by 2. Now this is 2 ln ap plus 1 equal to minus ln v plus constant. Now this constant we call as ln v, so that this whole term can be having a compact form. So this is 2 ln ap plus 1 equal to minus ln v plus ln v. So you are getting ln v plus 2 ln ap plus 1 equal to ln v. So now combine together that ln a plus ln b is ln of a into b. So this is ln of v into now again this thing 2 ln ap plus 1 means this is ln ap plus 1 whole square. So this is ap plus 1 whole square equal to ln b. Now we can directly simplify and give it a compact form, that this is v into ap plus 1 whole square equal to some constant equal to b. This is the equation for adiabatic curve that is asked in the question. Let us go and match whether our answer comes right or not. So this is option number C, D. V ap plus 1 whole square equal to constant. So this is also the accepted answer. So our formulation is correct. Now move on to question number 5. Okay. So question number 5 is about you have been given a diagram in t versus s plane. Okay. T versus S diagram, and the efficiency of the so basically it is a T versus S diagram where a reversible engine cycle is shown by that diagram, And reversible engine, that you already are familiar with from the earlier session, earlier week's lecture also. But now the newness of this is that now this thing is represented by a TS diagram, and from the diagram you have to know every information you can get about that engine. So basically they are asking you the same, that by seeing this diagram they are asking you that if this is the diagram of a reversible engine cycle, then what is the efficiency of the engine that you can get from here. So this will be an interesting question, because you know that efficiency of any engine is equal to basically the work output that we get from the engine divided by the heat input to that engine. So output by input, output is in terms of work done, which is basically the heat getting partially converted into work by that engine, divided by the energy input, which is basically the heat that is absorbed. So these are the two forms for getting the efficiency. Now we choose a blank page and start this calculation. That this is question number 5. This is T versus S. Now this is like a triangle that they have given for the engine cycle in the question, and it has the points of the triangle are mentioned in the ATS diagram. This is S1 and this is 3S1, and the top point is on 2S1. Also this and this is your T1 and this is your 2T1. Now let us mark this triangle as ACB. Now this is a engine cycle. This is a reversible engine cycle represented as TS diagram. Okay. Now we have to calculate what is the efficiency of that engine. Efficiency equal to work output W by heat absorbed input, which is Q1. So you know that reversible engines are basically like Carnot engines, and Carnot engines work in this way, that you have your hot end at T1 temperature and you have your cold end at T2 temperature. So this is T1 greater than T2, this is hot and this is cold, and this is the engine that is connecting these two. So it will be absorbing Q1 amount of heat from the source, which is the hot end at T1 temperature, and that heat will be partially getting converted into work done, which is W, work output from the engine, and the remaining amount of heat, that is Q2, will be again dumped into the cold body. This is the working principle for a reversible engine or like a Carnot engine. So in this case your work done W is nothing but Q1 minus Q2, and your efficiency is W by Q1, which is W by, if you know your work done, then Q1 simply can be W plus Q2. So W by W plus Q2. Now here the catch is that when you have such a TDS diagram, so the first thing you have to know is that whatever shape that the diagram is given in, but the area, but the area which you have inside this plot, okay, this is the yellow area that I am marking right now. Okay, so the boundaries are now not seen, so let me draw them once again. So this was our triangle boundary ACB, right, and this is your this 2S1 line. Okay, so this area is your work done W. So if you calculate the area of the triangle, you will be getting the work done from this engine. And the other thing is that if you look at this AB part, So the engine is a reversible engine cycle, right? So it can go on in a closed cyclic manner. So you can get like this to this to this and again coming back. So this is like a cyclic thing. Okay, so if you just look at this AB part, so you will see that AB part is at a constant temperature thing, because this is just a parallel line to the x-axis, which is entropy axis. That means here the temperature, that is the y-axis value, is constant. So throughout AB, this is isothermal and its temperature is equal to constant at T1. And as per the diagram, this T1 is the lower temperature end and 2T1 is a higher temperature end. So at C you get to the higher temperature end, but during AB, temperature is fixed at T1 and it is the lower temperature end. That means it is at the cold body side, right? So as per the Carnot engine's formulation, at the cold body part at the lower temperature T2, you have the heat being dumped. So in this point, in this process of A to B, your heat will be going out or released from that engine, right? And so basically, if AB is the part where your Q2 heat will be released in the cold body, which is at a lower temperature, that is T1 in this case, then if you just integrate out what is the area under this AB line as in the TDS diagram, so you will be getting your heat that is released to the cold body. So what is this area? This area is this rectangular shaped under AB. So area under AB line in TS diagram is equal to heat being released into cold end at lower temperature. Here the lower temperature is T1. So this might cause confusion because they are also mentioning the markers as T1. So instead of the Carnot engine's general formula, we do not write T1 and T2 because that may create confusion whether this hot temperature end here is T1 but here the lower temperature part is T1. So this might create confusion. So we change our notation as TH. TH means the T hot part or the hot body's temperature, and the heat input is QH, and the heat that is being dumped is QC, that means Q cold, and this is TC means T cold, the cold body's temperature. So TH is greater than TC, and so basically W work done is equal to total heat absorbed QH from the hot body minus the heat dumped to the cold body QC. So QH is nothing but W plus QC, and your eta is W by QC, which is W by not QC, W by QH, and which is just W by W plus QC. Okay. So here in this case here TH equal to 2T1 and TC equal to T1, which is the hot body part is 2T1 temperature, higher temperature, and the cooler body part TC is at T1 temperature. So that will be the point where the heat will be dumped into the cold body. So you have to calculate what is the area under the AB line in this TDS plot. This is simple because this is just the area of a rectangle which has one side as this 3S1 to S1 is 2S1, and the other side of the triangle is just T1, which is the height in this case. So this area of the rectangle has two sides, T1, the other side is 3S1 minus S1, which is 2S1. So this is 2S1 T1. Alright, so 2S1 T1, and so your this has been the QC part, that is the heat that is being dumped into the cold body. Now you are yet to calculate the area of the triangle, which is your work done from the TS diagram. Area of the triangle ABC equal to work done by the engine, that is W, which is triangle's area is half into the base length, which is AB, into the actual height, which is, in this case, let's say this is O, so this is OC. So half into AB into the height OC, and AB is basically again 2S1, because this is S1 to 3S1 is 2S1, and the height here is this part is nothing but your T1 to 2T1, right? So this is the difference, this is the height part. So this OC is T1 to 2T1, which is 2S1 into 2T1 minus T1. This is just S1 T1. This is W. So your QC is done and W is also known. So QH is nothing but addition of both W plus QC equal to S1 T1 plus 2 S1 T1 is equal to 3 S1 T1. So your efficiency eta is W by QH is S1 T1 by 3 S1 T1, which is 1/3. Right? So 1/3 is your answer for efficiency from this plot. So let us go back and check. So you are getting 1/3 is the right answer. So this is the accepted answer, right? Now, sixth question is, an isothermal curve and an adiabatic curve in PV plane corresponds to dash and dash in TS plane respectively. So isothermal curve, right? That means temperature is constant. So first of all, isothermal, what it would look like in the PV plane? In the PV plane, it will be just like PV is equal to constant, because temperature is constant. So then the isothermal curve will just look like this, a rectangular hyperbola in the PV plane. But in the TS plane, which is an alternative expression for the processes, because P and V, their multiplication has the same dimension as T and S. Okay, so thermodynamic representations are different, but they can represent the same process differently. Like isothermal process for TS diagram will be like a constant line parallel to the S axis, entropy axis, because on each point on this line, wherever you go, the temperature is, if this point is T naught, so then everywhere that temperature is T naught. So this is just a constant line parallel to the entropy axis. So this is the isothermal process in both PV and TS diagram. So first one is chosen, and the other one is, what is the adiabatic curve that will look like in this case. So adiabatic curve for PV diagram is basically, you know, adiabatic equation is PV to the power gamma is equal to constant. So difference from isothermal to adiabatic in the PV case is that its slope will be much steeper. Okay, so if this is adiabatic, then isothermal may be here, much lower slope. But because this is PV to the power gamma equal to constant, so this is adiabatic, this has a much higher slope or steeper than the PV equal to constant, which is the isothermal one. And the adiabatic curve, looking what it would look like in TS plot, is basically, adiabatic means your dq equal to 0, no heat exchanged, and you know that dq equal to just T times ds. So if dq is 0, T times ds is 0, and the temperature is finite, so T not equal to 0. So the only explanation is ds equal to 0, or your entropy S equal to constant. So adiabatic process ensures that the entropy is constant. So how you will get an entropy constant in the TS diagram is very simple, that you will be getting a parallel line, straight line parallel to the temperature axis, because this is our entropy, let's say S1. So all through point on this line will have the same entropy S1. So our answer will be, for isothermal curve, it will be a straight line parallel to entropy axis, and for adiabatic curve, it will be a straight line parallel to the y or temperature axis. So this is the accepted answer, right? Now, question number 7. Just 1 second. Okay. So now question number 7 is based on auto engine. This is a different kind of engine that has a efficiency formula and working that is different from a Carnot engine, which is a simplified case of reversible engine. But this is an auto engine which is discussed in this week's lecture materials. You can check the formula etc. from there, because there is nothing much to solve in this case. We will just directly use straightforward formula that is known to us for such engines. Okay. So question number 7 is the auto engine case, that the air intake takes place at 1 atmosphere pressure at 30 degrees centigrade. Before the ignition, the pressure of the combustion chamber is 16 times the initial pressure. Then find the compression ratio if gamma is equal to 0.5, 1.5. So let us choose a page. Yeah, so this is question number 7. Problem is based on auto engine. So just for simplicity, we'll draw a very schematic graph diagram of the auto engine's PV diagram schematic. Okay. This you can also find in the lecture material itself, but I am just drawing it because that makes easier for us to understand the problem. Okay. So let's say going like this and then going like this, this again a cyclic process, and then again coming back like this. So this is, mark different points as P2, P1. This is point number 5. This is 1, 2, 3, 4. This is at P1 and this is at P2, and this pressure is P3. This is V2, V1. So here the heat is being absorbed in this part, that is QH, then getting converted into work on this 3-4 process, and the remaining heat is again being released to the cold body as QC on this 4-1 part. Okay. So here the intake stroke is the 5-1 isobaric process. So 5-1 is the intake stroke, which is the isobaric, where the pressure is constant. So as per the question here, because it is isobaric, here the pressure is constant as 1 atmosphere, right? And it is mentioned that before ignition, the final pressure is 16 times the initial pressure. So here the 1 to 2, this curve is basically an adiabatic curve. Okay. In the PV diagram, it will have a formula of PV to the power gamma equal to constant, where the gamma value is given in the question as 1.5. So 1 to 2, it is adiabatic, and here it is called the compression part, because the volume is decreasing from higher volume V1 to lower volume V2. So, and the pressure is changing also from P1 to P2. So because it is a compression, the pressure will be rising. So the final pressure is P2 equal to final pressure in compression. This will be greater than the initial pressure, and as per the question, this is 16 times the initial pressure P1. So P2 equal to 16 times P1, and because it is a compression, the final volume is lower than the initial volume. And you have to calculate what is the compression ratio, or how much, by what amount that volume is getting compressed. So compression ratio, we call it R. R is nothing but V1 by V2. So this is the initial higher volume divided by the final lower volume. This gives you your compression ratio of R equal to V1 by V2. Right. So in this case, now because this is adiabatic, so this is PV to the power gamma equal to constant. So we can write P1 V1 to the power gamma equal to P2 V2 to the power gamma, right? So now V1 by V2 to the power of gamma will be P2 by P1, which is basically 16 P1 by P1. So this is just 16. Now V1 by V2 to the power of 1.5, that's the gamma value, equal to 16, and then V1 by V2 will be like 16 to the power 1 by 1.5. Now 1.5 is 3 by 2, so 1 by 1.5 is 2 by 3, which is around 6.35 by calculating. So your compression ratio V1 by V2 is 6.35 for this auto engine. So we have just directly used the formula that we know for the adiabatic curve. We just have to know the different points where the compression is happening, how the adiabatic curves are related in the volume and pressure on different points. Those are the main concerns. So our result is what you get is 6.35. So this is also the accepted answer. Now question number 8. If the compression ratio of a diesel engine is 15 and the fuel cut-off ratio is 3, then find the efficiency of the engine. Again, it is about a different engine which is different than the other auto engine that we have just discussed. This is a diesel engine. Again, this is also discussed in detail, elaborate details in the lecture material. You can find that out. But for us, we will directly be using the formula that is mentioned there. So two informations are given. Compression ratio is 15 and fuel cut-off ratio, which is a new thing that we did not learn in the last engine, auto engine. This is new for the diesel engine part. That is 3. Then find out the efficiency eta for that engine. Okay, so this engine's efficiency formula is already there in the lecture. So let us remember or recapitulate that and directly use that for the solution. So I'll be again for the reference showing a brief schematic, but this is not necessary, but I suggest that this is useful to do because every time you have the schematic in mind, basically the ideas are clear to you how the engine operates, and even if the straightforward formula type of question does not comes as a numerical problem, even after that you can understand what is being asked in the question and you can answer accordingly. So that is why I prefer to draw it with the diagram every time. So this is for a diesel engine where this is a PV diagram, right? And this is so the drawing may not be very accurate, just take the idea. It's going like this. Okay, this is 0.5, this is 1, 2, 3, 4, and the different point values of the parameters of volume and pressure are marked. Like this is V2, this is V3, this is V1. Okay. Now here for this case, this 3 to 4 is your adiabatic part. Okay, adiabatic curve, and the work is done as the output from this engine from here 3 to 4, and the higher temperature side is 2 to 3 where this is a constant pressure part, isobaric, and here the combustion happens, so heat is being absorbed on this part. So here the combustion happens on 2 to 3. This is an isobaric process, and after work output the excess heat has to be dumped into the cold body. So 4 to 1 is basically that. This is the isochoric process, or the volume is constant, isochore, but here the heat that is being dumped into the cold body, QC, that is being released. Okay, now the different definitions, like the compression ratio equal to R equal to remains the same, that V1 by V2. So 1 to 2, its volume is compressed, that compression is V1 by V2 is measured by the compression ratio. And the other thing, fuel cut-off ratio is marked by rho equal to nothing but V3 by V2. So this another volume V3 and V2, so between 2 and 3, this ratio is given by this fuel cut-off ratio rho. Now as per the question, R is 15 and rho is 3. Now efficiency of a diesel engine Eta has a direct formula that we'll be using. Also gamma for the adiabatic part over here is 1.5. Now you know the efficiency formula, you can see from the lecture material that it is 1 minus 1 by r to the power gamma minus 1 into rho to the power gamma minus 1 divided by gamma rho minus 1. So this is 1 minus 1 by 15 to the power gamma is 1.5 minus 1 into rho is 3 to the power gamma 1.5 minus 1 divided by gamma is 1.5 into rho is 3 minus 1. So what we are getting is 1 minus 1 by 15 to the power 0.5 into, you can calculate this and you will get, can calculate this and you will get 1.4. So this will give you 0.64, which is 64% efficiency for the diesel engine. So let us check the question and match the answer. 64% is what we are getting. This is option number C, also the accepted answer. So this is done. Then question number 9 is again a direct formula based question. Here again diesel engine based question is given that the compression ratio R is given as 22 if the temperature of the fuel before and immediately after the combustion is 647 degree and 1751 degree respectively, then what is the efficiency? Okay, so here you have to also have the information about the temperature before and after the combustion. From there you have to basically calculate that this fuel cutoff ratio, because it is not directly mentioned in the question, and then again using the same efficiency formula you can calculate what is your efficiency. So let us choose the page. Yeah, so this is question number 9, again based on diesel engine, right? So the compression ratio R is equal to V1 by V2 given by 22 now in the question. Fuel cutoff ratio R rho is equal to V3 by V2, but that is not known to us right now. Rather what is known to us is that before combustion temperature is, so now the schematic will come handy, because that is why you will be benefited if you remember the schematic, or if you try to solve the problem every time you draw a schematic. So here this combustion process is happening between 2 and 3 points. So 2 to 3 is the path for combustion where the heat is being absorbed in the system. Now this 2 to 3 has volume of V2 to V3, that actually relates your fuel cutoff ratio, because that is a ratio of V3 by V2. Now you don't have the information about V3 and V2 values, but you have the information about their temperatures. So like before combustion if the temperature is T2, and after combustion at 3 if the temperature is T3, then you know the T2 and T3 values from the question given. So your T2 value is basically before combustion, which is 647 plus 273 in Kelvin, and T3 after combustion at the point 3 the temperature is T3, which is 1751 plus 273 Kelvin. Now because this, just see that this 2 to 3 is a isobaric process, that means the pressure is constant, right? So 2 to 3 is a isobar where pressure is constant. So for ideal gas, if you have the pressure constant, so you will be using the Charles law, that at constant pressure the V by T ratio is constant. When pressure equal to constant, so V by T ratio is constant. That means your between the 2 points 2 and 3, the volume, if that is V2 by V3, then it will be same as T2 by T3. But because your fuel cutoff ratio is V3 by V2, so we directly calculate that. So V3 is equal, rho is equal to V3 by V2 equal to T3 by T2, which is the final temperature is higher. So this is 1751 plus 273 divided by 647 plus 273. So you'll see that this value is almost 2.2. Now if that is the case, now you have the information about rho. You already have R known from the question is 22. So direct efficiency formula is there. The same formula, 1 by R to the power gamma minus 1, then rho to the power gamma minus 1 by gamma rho minus 1. Sorry. So then eta for the diesel engine will be 1 by R is 22 to the power gamma minus 1 is 1.5 minus 1, which is 0.5 into rho is basically 2.2 to the power gamma 1.5 minus 1 divided by gamma is 1.5, rho is 2.2 minus 1. So by carefully solving it, will be getting 0.65, which is 65% efficiency of the diesel engine. So let us check the answer. Okay, so answer we are getting is 65% and that is matching with the accepted answer. So this is done. Now the final question is question number 10, which is basically calculate the efficiency of an engine with an ideal gas operating in the cycle as shown in the figure below, which is a PV diagram, and the ratio of the specific heat gamma that is given as 1.4. So if that is a cyclic process of how this engine is working, so from this PV diagram you have to calculate what is the efficiency of the engine. Right, so again you know that to calculate the efficiency, every time you have to get the work done divided by the heat absorbed, right? So for this process it will be the same. You have to calculate that first, the work done and the heat absorbed, and we already know this idea is clear to us that um, like this is a cyclic process, and you can see that this is not an exact triangle, so you cannot directly very easily calculate the area under the curve like taking a triangular area, because this B to C is a curved line, so this is not a straight line. That makes ABC not a triangle. But so calculating its formula, area formula is not straightforward, so we have to directly and explicitly use the formula of work done and sum up the work done for all the three stages of this cyclic process. Like ABC has three parts, C to A to B and B to C, and we have to combine all of the work together from these three stages, and then we can get the total work done, right? So let us choose a page because this can take some space. Yeah. This is the diagram. This is A, this is C, and this is B. Okay, this is a P versus P diagram. And as per the question, this is the volume V0, this is 2V0, and this is a pressure of 3P0, and this is P0. So as per this question, it has three steps: C to A to B, and B to C. C to A, you can see this is a line parallel to volume axis. That means here the pressure is constant. So this is the isobar where the pressure is constant at P0, and the volume is changing from 2V0 to V0. So this is a compression process. And A to B is a parallel line to P axis. So here the volume will be constant. So this is the iso core, and the volume is fixed at V0, and the pressure is changing from P0 to 3P0, right? Finally, B to C is adiabatic process, that is already marked in the question itself, and the formula here will be PV to the power gamma equal to constant, right? Now first you have to calculate the total work done. That will be a summation of WCA plus WAB plus WBC. Now WCA is where the pressure is fixed at, so you know that W formula is PdV, simply pressure into volume change. So along CA the pressure is fixed at P0, but the volume is changing from 2V0 to V0. So final volume is 2V0 minus initial volume V2, final volume is V0 and the initial volume is 2V0. So this will give rise to a negative work done, but this is the work done on the path CA. Plus AB is a path where the volume is constant at V0. So here the pressure is changing but the volume is constant, so PdV is 0, so WAB is 0. So for an isochoric process and the volume is not changing, so then the work done will also be 0, so it has no contribution to work done. And finally BC for the adiabatic path. So you know the formula of adiabatic work done already from our earlier lectures and earlier tutorial series, so I'll be directly using that adiabatic work done formula, that W adiabatic is the work done for adiabatic process is Pi Vi minus Pf Vf by gamma minus 1, where Pi and Vi are the initial pressure and volume and Pf Vf are the final pressure and volume. So if that is the case, then WBC is just where at B the initial pressure is 3P0 and the initial volume is V0. So this is 3P0 V0 minus at C the final pressure is P0 and the final volume is 2V0. This is 2P0 V0 by gamma value is given in the question as 1.4. So 1.4 minus 1. So the first part is minus P0 V0 plus second term is 0 plus P0 V0 by 0.4. So this is minus 0.4 plus 1 P0 V0 by 0.4. So this is 0.6 by 0.4 P0 V0. This is 3 by 2 P0 V0 or 1.5 P0 V0. This is, sorry, so this is your, again, so this is your work done. So one part is done. Now you just have to take the, what is the heat absorbed in this case, right? Now you have to look at the graph. So in the PV diagram you can see that the work is being done from this adiabatic curve. So work is being done. Now the earlier two parts are, the other two components has to be done from there. So your heat has to be absorbed from this A to B part, because that is just before the work is getting, the heat is being converted into partially into work. So this is the QH being absorbed, and after it is getting partially converted into work done, it is again releasing the excess amount of heat as QC. So AB is the part where the heat is being absorbed in the process, and AC is the part where the heat is being released to the cold body in the process, right? Now to calculate what is the heat being released, so you have to just calculate what is the area that is just under this line AC. Okay, and that will be simple. You can get QC just by taking the area under this, but then again there is also a catch, because now you have to also consider okay, so let me frame it like this, that you are getting your work done as 1.5 P0 V0. Okay, so instead you cannot do it like that, but you have to take out the QH from here only, because your eta is nothing but your W by QH, right? So W you have already obtained, you need QH. So QH is on the AB path, but this is a PV diagram, so you have to take into account directly by calculating the heat absorbed in the QB path. So Q on AB path is basically coming from two parts, one is du, other is dW, okay, on the AB path. Now du is the internal energy change, which is nothing but CV dt on AB, And because AB is a constant volume process, so PdV part is here 0. So there is no work done. So dW equal to 0. Only from the temperature change you will be getting a heat. So here we know that Cp by Cv equal to gamma and Cp minus Cv equal to R. Right? But also for ideal gas, PV equal to RT, we are taking 1 mole, N equal to 1. So if only pressure is changing along this AB path and volume is constant, so we take the derivative on the pressure and keep the volume constant, and the temperature is changing, so dt on the other side and R is constant already. So dt is nothing but your V by R into dP. So we are changing from temperature to in terms of pressure because volume is constant on AB, right? So this is Cv, replace this here, Cv into V by R dP. Now Cv into V is constant at V0 here, so we take it outside the integral, and the other constant terms are also outside integral, and only dP is here. So this is Cv times V0 by R into the pressure change. So along AB, so going from A to B, the pressure is changing from P0 to 3P0. So this is 3P0 minus P0 then. So this is 2P0 into V0 into Cv by R, right? Now if Cp minus Cv equal to R for 1 mole and Cp equal to gamma Cv, then gamma Cv minus Cv equal to R. So Cv times gamma minus 1 equal to R. So Cv by R is equal to just 1 by gamma minus 1. So that we replace here, 2 P0 V0 into 1 by gamma minus 1. So you get 2 P0 V0 into 1 by 1.4 minus 1 equal to 2 P0 V0 by 0.4. So from here you get 2 by 0.4 is 4 by 10. So this is 5 P0 V0 that you are getting as your heat being absorbed in this cyclic process. So and W was earlier to be calculated as 1.5 P0 V0. So your efficiency of this engine is 1.5 P0 V0 by 5 P0 V0. So this is cancelling out. So this is just 0.3. So your answer for the efficiency is 0.3. So let us go and check. So the answer is 0.3, which is option number C. Okay. So with this we are done with the 10 practice problems. Now this is where starts the current assignment problem, which you are given to solve as a part of the course. Now if I just look at it in a way that you see that most of the questions are common, right? Like just go towards the lower part, you will see that many questions are common. Like this question number 4 is already solved. So this is done already. Question number 5 is again common. Just remember this diagram we just solved before in the practice set. So 4 and 5 are common. Then 6 is not common, but 7 is the auto engine problem common, diesel engine problem 8 common. Then 9 is again the second diesel engine problem, which is again same. 10 is also common. So total these are the problems which are common to us between the two assignments, and the new problems are 1, 2, 3 and 4. Just 4 problems are new. So I'll be briefly discussing how to solve these problems, and you can try it for yourself to solve and attempt to solve this. So the first one is calculate. One second. First one is calculate the change in entropy when 10 gram of ice at minus 10 degrees centigrade is converted into steam at 100 degrees centigrade. I think similar type of problem we have solved before in a past assignment, I think in week 8 in only. So you can try it by yourself. This is just a simple formula of entropy change. So entropy change can happen by two things. One is change in temperature and the other is heat absorbed in change in phase. So in going from ice to water, ice to steam, you go through several steps. One is ice temperature is changing from minus 10 degrees centigrade to 0 degree centigrade. Then the phase change is maintaining the same temperature of 0 but changing your phase to water. Then changing your water temperature from 0 degree centigrade to heat it up to 100 degree centigrade at the same phase. But then ultimately keeping the temperature constant at 100 and going from water to steam. So delta S is a summation of all four parts. Okay, delta S1 plus delta S3 plus delta S4. These are the summation for all four parts. And you know how to calculate the entropy for change for temperature change. This is simple. This is just MC ln of Tf by Ti, where m is the mass, C is the specific heat per unit mass, and Tf and Ti are the final and initial temperature. So this is when the temperature is changing. And all the relevant components are values are given to you, like the mass or the specific heat for what ice in this case is given in the question. And when you have to calculate what is the specific heat for when heat is being absorbed for a phase change, like for ice to water you have to absorb some heat, and that is basically your latent heat where the temperature remains constant. And latent heat is also given in the question in terms of per kg unit, so you have to take care of the unit and multiply it by the mass. So this is if the specific heat of ice the latent heat of ice to water is L1, so this is m L1 by the constant temperature is T0, which is 0 degree centigrade. So this is the specific the entropy change for this phase change from ice to water. Then again for the third stage, when the water temperature is changing from 0 degree to 100 degree, again using the same formula, only the specific heat of water you have to use now instead of ice. Then the final temperature is 100 divided by initial temperature T0. Remember, all these temperatures will be in Kelvin units and not degree centigrade. And final, the phase change from water to steam is, let's say, mass times the latent heat of water to steam phase change. Let's say it is L2 and the temperature is fixed at T100. So by maintaining the units properly and calculating by using the known quantities all given in the question, you will be adding these four terms and you will be getting your final delta S. And if you do your calculation correctly, I think the value will come. So let me not give you the value, we'll find out because I have already shown you how to solve this. Okay, so this is done. Now the second question is again a diagram based problem. So these are many commonly coming. So by now you have to get a hand of it how to solve these kind of problems. But this is again the efficiency of the cycle has to be calculated, where the first case has the efficiency eta 1 and the second cycle has the efficiency eta 2, and you have to find their ratio. So the idea is mostly simple, that whenever you have been given a TDS diagram, always remember that area of TDS plot will be giving you a work done directly. And if, like in these cases, when the area is just a simple triangle and you know how to calculate the area of triangle, half into base length into the height, and these are all right angle triangles, so you already know from the TDS plot that what is this value and what is this value, or what is this length and what is this length, and then half into this length into this length, you will give you a triangle's area, which is the work done in all cases for TS diagram. So work done from here will be obtaining from area of this, and also the area of this will be giving you a work done here. Now for efficiency you also need the heat that is being absorbed, like QH. So how do you calculate QH? So like in this case I have also discussed earlier that this T1 is lower than T2, so T1 is obviously a lower temperature side, and you know that on the lower temperature side is when the heat is being dumped into the cold body. So here this will be the QC coming out of the system along the path BC. Okay, and so if you just take the area under this rectangle, the rectangular area that you are getting under BC line, so that will give you a value of QC. So this dashed line under BC is your value of QC, and you know the W from the triangle's area. So your QH will be simply addition, sum of both. So W plus QC, which is area of triangle ABC plus area of this rectangle. And if you sum up those, you will be having QH, and you already know W. So eta 1 will be simply W by QH. So that is one thing that will be getting from here, first cycle. And for the second cycle, again, your work done is again the area of the triangle that remains the same. Now what is the heat absorbed in this case, right? So heat absorbed here will be on the high temperature side. So this is just a inverted version of this part, right? So now the high temperature side is T2 and this side is AB. AB is the line when the heat will be absorbed into the system, because this is the high temperature part which works like a heat source. So the QH heat comes into the system from AB part. So then by calculating the area under this AB line, you will be having the rectangular area, this whole area up to this, you will be having your value of QH, and from the triangle you will be having the value of W. So then the eta 2 will be that W, the area of this triangle, by QH, this is the total rectangular area, and then by taking this ratio you will be having one of these answers. So this is again this hint I have given how to solve this. Then question number 3 is that find the entropy increment of an aluminium bar of mass 3 kg. So mass is given in SI units, 3 kg. Sorry, this is, yeah, so this is mass is given 3 kg, and it is heating it from 300 to 600 Kelvin. So in the temperature interval, the specific heat capacity varies. So this is not constant, but this is the temperature function. So this is A plus BT, where A and B values are given, but just remember that you have to maintain the same unit. So be very careful of the units, because here the mass is in kg unit, but the A value is given in joule per gram Kelvin unit. So this gram you have to consider that this is kg, so you have to convert it into gram, so that this gram and this gram can match. Similarly, for B value it is given in millijoule per gram. So gram is taken care of if you convert just this kg into gram by 3 into 10 to the power 3 gram. But this is millijoule, so you have to take care that this is also in joule units, right? And the idea of entropy change is the same, because only the thing that is different is that now you cannot take the C out of the integral, because this is not constant, this has a temperature dependence. Otherwise your delta S is again dq by T, which is m C as a function of T dt by T. Now only m is constant, so it comes outside the integral, and A has a temperature, C has a temperature dependence, A plus Bt by T dt. So this is m A by T plus B dt, and your temperature is going from Ti to Tf, where Ti is your 300 Kelvin and going to final temperature of 600 Kelvin. So this is m A ln Tf by Ti plus B times Tf minus Ti from the integral. Now you can just carefully substitute the values, all maintaining in the same units, and you will be having the answer if you calculate that carefully. Now this is also done. And the last question that is uncommon from the practice problem, I will be giving the hint to you too, is this question number 6. Is 40 gram of water at 50 degrees centigrade is mixed with 80 gram of water at 20 degrees centigrade. Then calculate the change in entropy for the entire water. So this is the similar type of problem, but one catch is that you have to use the thermal equilibrium condition, that when these two waters of different temperatures are coming into direct contact, so they will be exchanging heat. So the thermal equilibrium condition is that heat that is absorbed by the hot body is equal, heat that is absorbed by the cold body is the same heat that is released by the hot body. So in this case, the first 40 gram of water has higher temperature 50 degree, so that will be releasing heat, and the second type of water having 20 degree centigrade is the cold water which will be absorbing heat. So if T1 is 50 and T2 is 20, you can convert it into Kelvin if you have to always maintain the absolute Kelvin scale. So T1 is greater than T2, and let's say the final equilibrium temperature is T for both. Equilibrium temperature for both. So the heat absorbed by the cold water is, the mass is 80 gram into, now again this has to be unit carefully consistent with that kilogram have to maintain, so 18 10 to the power minus 3 kg is the mass, into the C, the specific heat of water is given in joule per kg Kelvin, so C is given, into the temperature change is basically, this is hot body, so this is T1 minus T. Then again this is the cold water, is, this is the heat released part, okay, and this is the heat absorbed part is 40 gram of water, 40 10 to the power minus 3 kg. C is same for both, so it can remain same, and the final temperature is now greater than the initial temperature, so T minus T2. So from here you have to calculate and solve what is T given in terms of T1 and T2. So then first you have to calculate what is T, and you will be seeing that your final equilibrium temperature for this case will be getting as 303 Kelvin from this calculation. Now once you do that, now the rest of thing is similar, that delta is equal to just delta S1 plus delta S2, which is nothing but your M1 C ln of T by T1 plus M2 C ln of T by T2. Now M1 M2 is known from the question, C is also known from the question, T we have calculated, and T1 T2 is known from the question. Just use Kelvin units and remember that all the units are consistent and you will be getting your answer. So the only catch here is that don't ever directly do the averaging of T1 and T2 as your final temperature. That only holds if both the bodies has the same mass, but in this case like they have different mass, 80 gram and 40 gram, so that will not work. Then your evaluation of the final temperature after the equilibrium will not be a simple average of T1 and T2 because masses are different on both sides, okay. So this is how, again, even if you have two different liquids, like one is water, one is, let's say, some other fluid, then both of them will have a different specific heat C. So then even C1 and C2 are different, so they also cannot cancel on both sides. So then again it will change, your final temperature will not be a simple average of T1 and T2. That is the most simplified case when you have mass and heat capacity same on both sides. So we can just directly take an average as the final equilibrium temperature. So with this we finish all the problems in this week's lecture, and we'll be doing next week's assignment in the next class.